This is a review for Chapter 6, Applications of Definite Integrals. The definite integral is applied for the computation of volumes, arc length, and surface areas. Here we'll go through these major topics for the chapter. Okay, now we begin with volume using cross sections. Suppose that we want to find the volume of solid like this one, and then we consider the cross section, and then now along with the partitions, this small portion can be approximated by cylindrical solid, or then along with the area of the cross section and with multiplication of the thickness will be easily computed. And so that here the Riemann sum can be formulated in this way. The area and then the thickness multiplication will be a local volume. The sum of this local volume is a good approximation of the original volume. So that is a Riemann sum, and along with the more partitions and taking the limit, we can find the volume. So that is called the method of slicing. So here, that is now definition. The volume of a solid of integrable cross-sectional area, AX, is now integral of the area over the interval. So the limit of the Riemann sum is now can be written in this way. Integral from A to B and area at each point X and dx. So that here we have a strategy for the computation of the volume of the solid. First, sketch the solid to understand. You have to understand the problem, and then try to find the limit of the integration, and for each point over the interval, try to find a formula for the cross section. So the area, and here after finding AX, just integrate to find the volume. Here B and C can be done simultaneously. Okay, let's look at this example. A curved wedge is cut from a circular cylinder of radius 3 by two planes. One plane is perpendicular to the axis of the cylinder, so that the one cut is like over the bottom is perpendicularly cut, and second one is cut with a 45 degree angle at the center of the cylinder, so that we get a curved wedge. We want to find the volume of the wedge here for this one. So if you can make the picture, then make a picture to understand the problem. Now here x is moving from 0 to 3 for each x, and here you have to find the area of the cross section, and for that one here the height will be the same as x because it's a 45 degree angle, and however this length must be in here twice of square root of 9 minus x squared. The reason is if you try to look at the wedge from the top, then there will be pictured in this way. Here radius 3 and right side, and this is now x-axis, and here So that is 3, and this is a minus 3 in y direction. Of course, in x direction, there is x. So that line is correspond to a line over there. Okay, this is now 3. So for each x, now this curve is, the top portion is same as y equal square root of 9 minus x squared, and bottom portion is now y equal minus square root of 9 minus x squared. So the length from here to there is twice of now square root of 9 minus x squared. And then this height is x. So that area for each cross section is this one. So your the volume must be obtained in this way. Integral from here 0 to 3, and x is moving from 0 to 3, and now there is 2x and square root of 9 minus x squared and dx, right? And of course you can get this one quite easily. Okay, that is now here 9 minus x squared and power, okay, 3 over 2, and along with a coefficient here. You have to decide this coefficient. Now, if you are making derivative for that term, then 3 over 2 will come out, and then now, so that, okay, and minus 2x will come out here, minus 2x, so that you have to put here now 3, okay, 2 over 3, minus 2 over 3. Okay, the coefficient must be minus 2 over 3, and here from 0 to 3, okay? So that you can get the solution here now, 2 over 3, and here times 27, okay? So that here 18 is the final answer. Okay, now we are using the method of slicing. However, now the shape, each slice is disc, then it's called the disc method. When a curve is rotated with respect to some line, then the curve will make a circle. Once you are considering the area, then area will make a volume, so that here, once the cross section is disc, then we say that is a disc method. So that is just through rotation is made, and then here cross section is pi r squared for each point x. Now pi r squared is the disc area. So area is just accumulated, summed over a to b through integration. Okay, so that's the idea of getting disc method. But in main principle, it's the same as here, integration of the cross-sectional area. Okay. Find the volume of the solid obtained by rotating the region between here y equal x squared plus, okay, x is y squared plus 1, and x is 5, and about, it's rotated about the line x is 5. Let's try to visualize to understand the problem. Okay, there is y-axis, this is x-axis. Now here, x is y squared plus 1. The curve is given in this way, like that. Okay, that is the curve. And here, x is 5 is this one. Now there is a 5. Now it is rotated about the line, x is 5. So this is rotated along with that line. Okay. So this region is rotated so that it makes a solid. Okay. So here, for this one, if we try to use disc method, then we may try to get the integration in y direction. So we have to find this bottom and top in y direction. Okay, x is here y squared plus 1, and x is 5. From this one, y is now plus minus 2. So that there is minus 2 and that's 2. Okay. Now, so that volume will be integration from here minus 2 to 2, and then a y. For each y, you have to find the cross-sectional area and dy. What is now a y? Okay. For each y, okay, that is now r. If you are choosing y here, then that is r is this one, because it rotated over there. Now, the distance is so that, okay, over there, now, from here, ay becomes now pi r squared. What is r? R is from here to there. So that is, in x direction is y. In x direction, that is y squared minus 1. So that this x minus that x. But this x is 5. This x is now y squared minus 1. So that is now here. R is, okay, 5 minus y squared plus 1. Right? Okay. So it is same as pi. Okay, that is y squared minus 4. In fact, it's 4 minus y squared. So that we can write here y squared minus 4 squared. So that is same as from integral minus 2 to 2 pi r squared. That is y squared minus 4 squared dy. So if you try to get the evaluation, then you'll get this one. You can do it yourself. And again, the same idea can be used for the computation of the volume when each cross-section is washer. And now, so that the larger one and minus a smaller one will be the required volume. Okay, let's see this problem. The region bounded by a parabola y equal x squared plus 1 and y equal minus x plus 3 is revolved about x-axis to generate a solid. Find the volume of the solid. Okay. Let's make a picture to understand it. Okay. Now here x-axis and y-axis. And the parabola is y equal x squared plus 1. So that y equal x squared plus 1. That is y equal here x squared plus 1. Now, y equal minus x plus 3. So, okay, and let's try to finish in this way. And there's 1. Now, minus x plus 3 will be given in this way. That is now 3. This curve is y equal minus x plus 3. So that region is now rotated about x-axis. So we want to find the volume of the solid. Okay. Now, so here, if we try to consider at each x, then here for each x here, now this region, this line is making a washer, so that's called the washer method. So here, washer area must be, okay, area of x must be here now pi capital R squared minus pi small r squared. What is capital R? That is this one. Height is now along with minus x plus 3. So that minus x plus 3 squared and minus pi. and small r is this one. So that is now height is x squared plus 1. So that x squared plus 1 squared. So here the volume is same as, okay, we have to find the lower bound and upper bound. How? By equalizing these two. So here now x squared plus 1 equal minus x plus 3. If we move this one on the other side, that one is x squared plus x, now minus 2 equals 0, and x separation, and 1 and 2 separation, and plus 2 minus 1. So here, that is minus 2, that is 1. Okay, the lower bound is here minus 2, and upper bound is 1. And then here pi is common, and then here that is now minus x plus 3 squared minus, here now that is x squared plus 1 squared, and dx. And then you will get this value. You can finish it yourself. Okay, let's go to the next section. Section 6.2, volumes using cylindrical shells. This is a different technique required. Okay, now we are to compute the volume of solid when a region is rotated by a line. So as in this figure, now this region is rotated about the vertical line XL. Then now we'll get a solid here. For the computation of volume, we first try to approximate the region along with a partition. So we try to make a partition, and then for each subinterval, we'll make a rectangular region. And then this rectangular region is now rotated so that each one will make here now a shell, so that this shell volume is added, and that will make a Riemann sum. So that is exactly when you do some detailed computation, then now that is here 2 pi r. So that is exactly now 2 pi r, and height and times the thickness. That is here thickness is that one. So local volume is now the length of this one, height times now that the thickness is good approximation. So for this quantity, we add them to get Riemann sum. Now we try to make partition with more subintervals and take the limit. Then that is that will be the volume. But in this technique, we are using now shell volume. Okay, here the formula for devolution about a vertical line, then that is now here. The volume must be integral from a to b, and 2 pi and shell radius, so the 2 pi r and shell height. So that once you consider this portion, then that is area of the thin shell when here you consider the point x, so that at for each x here you have to find the 2 pi r and shell height. That is really the area of the thin shell. Okay, let's try to solve the next example. Okay, the region bounded by the curve y equal square root of x, and the x-axis and line x equal 4 is revolved about the x-axis to generate a solid, we want to find the volume of the solid by using the shell technique. Okay. Here, and exactly same way, we have to understand the problem. So let's draw a picture. Now, yeah, that is y-axis, that is x-axis. Now, for this one, y equals square root of x, so that we have y equals square root of x, that is y equals square root of x. And then an x-axis, and x is 4. So that is now x is 4, and x-axis, the region, this region is rotated about x-axis, yeah? So it is making a solid. For that one, we want to use a shell technique. Then, now, shell is made, if you consider x directional integration, then for each x is a vertical line will make a disk. It's not shell technique. Okay, shell is made for each horizontal line. Shell is made for this one, so that for each one will make a shell, so that we have to make integration from 0 to here the y value and in y direction. So let's try to find this one. When x is 4, then y is 2. Okay, so that the volume is the same as integral from 0 to 2, and now 2 pi r, and now here, okay, let's say that is height. So that that is area of the shell at each point of y, right? Okay, we'll figure out what r and h could be. Okay. Now r itself is now for each y, r itself is y, right? And what is h? H is from here to there. Okay, we have to express this height as a function of y. Okay, now this is x-directional the length. So here, that is the same as basically y squared equal x. From this x and to this x, and there's a length. So that is exactly now 4 minus, and here that x is the same as y squared. Okay, so we found everything. So here volume must be from 0 to 2 and 2 pi and y, and here 4 minus y squared and dy, right? Okay, so if you try to evaluate this one, you'll get that one. You can finish it yourself. Okay, now here we'll go to areas of surface of revolution. In section 6.3, and differential of arc length can be expressed in this way. ds is square root of dx squared plus dy squared. It can be written in x direction, and it can be written in y direction. Okay, along with dx and dy. Okay. Now, for the area of surface of revolution, we need some knowledge from the surface area of first term. Okay, here for this first term, the surface area, the side here, the curved surface area is now 2 pi and average r, average radius, and here that length, the side length is this one. So 2 pi average r, capital R plus small r divided 2, and now the length is the side length. So along with this one, now we can get the surface area for revolution about x-axis. Okay, this curve is rotated with about that x-axis, then now surface is made. Now after partitioning, rather than this portion, and we may try to consider this straight line, and then that is revolved, so that rather than local real surface, we consider the surface of the curved surface of frustum. So this frustum can be the area of this frustum surface area can be good approximation of real the surface area. So here the strategy is start with partitioning and approximation along with here straight line, and then for each frustum, each partition, we have a frustum, and then now the surface area of the frustum must be computed. That addition is Riemann sum. So here we have, by using the formula, now 2 pi, the average height, and now that is here length. That length is this one. So that is same as square root of 1 plus f prime squared and dx. Right? So also it can be approximated rather than here average height, the average radius, we try to use at some point the f value. So that is now a Riemann sum, and once you take a limit, then ck will be changed into the x, and delta x will become a dx. So here we have the formula as a definition. The surface area for revolution about x-axis. Then here it is now integration must be in x direction and a to b. Now the radius will be y, so the 2 pi y, and that is now this portion is length, so that is a sort of a ds part. So then square root of 1 plus dy over dx squared and dx. So y is f of x, so that is now it must be expressed as a function of x, so that we write down the detail. If it is revolution is happening about y-axis, then now integration is in y direction. Again, this is from c to d, and the radius is, in this case, radius is x, so that 2 pi x, and this portion is now same as ds. Okay, so we have to express everything as a function of y, so that we reach at this one. Okay, now the main idea of surface area computation is here 2 pi r and ds. That is a main formula. Area surface can be obtained along with that formula. Now, when the given curve is monotone such that it is inverse, then let's consider here f is ascending from a to b, and domain is a to b, and the range is c to d, then its inverse is from c to d to a to b. Then now, and once we rotate about y-axis, okay, rotation is about y-axis, and then in this case here radius must be x, so that here now 2 pi r ds, okay, that one is now radius is x, and here we can write this one as a function of x. So that is x direction integration. But for that one, you can make also y direction integration. Now, so that everything must be written as a function of y. Now that one is 2 pi, again r is x must be here g of y. From this one is inverse, then x must be g of y. Again, that is the same as, in fact, x, and it's coming from r anyway. And then, now, this portion is a ds. Okay, ds can be written in this form, in this form. So that even though rotation is about y-axis, you can integrate this one in x direction or y direction when you can express the curve in its inverse form. Okay, now let's try to solve this example. Find the area of surface obtained by rotating the curve y equal x squared about y-axis. Okay, we'll try to get the area along with x integration and y integration. Okay, here, first we have to understand the problem. So start with the figure. Now, y equal x squared. That one. That curve is y equal x squared. X is moving from 0 to 2. That is now rotated about the y-axis. So that we have now surface made. Okay. So we will do first x integration. That is now, okay, for the surface area, okay, that is, in x integration, it will be from 0 to 2. And then, now, that is 2 pi. Radius is x and ds. Right? Okay, for this one, now from 0 to 2 pi, okay, x. That will be changed into as a function of x, which is exactly over the square root of 1 plus f prime of x squared dx, right? Okay, so that is same as from 0 to 2 and 2 pi x and square root of y equal x squared. That is f of x. So that here 2x squared, so 1 plus 4x squared dx. Now, from this one, you can get the integration quite easily. Okay, how about y integration? Now, for that one, once x equal 2, then y equal 4 here. And also, now, x is radius, so that x is now square root of y. So that the surface area is same as, anyway, let's start with here from 0 to 4, and that is 2 pi r ds. Okay, r is x, so that must be square root of y. And so the r must be square root of y. And then now ds must be here. Okay, it must be expressed as a function of y. So that, okay, so that is now xy derivative. So square root of 1 plus xy derivative, which is same as 1/2 and, okay, 1 over 2 square root of y and squared. Okay, and now that is ty, right? So here we have the surface area is same as from 0 to 4 and 2 pi and square root of y, and here square root of 1 plus 1 over 4y and ty. Okay, it's not so difficult to get the antiderivative we can combine them. Then it's same as from 0 to 4, and 2 pi is there, and we combine, and that is same as here y plus 1 over 4, right? Okay, its antiderivative can be easily found. So if you finish the computation, then from both sides you'll have the same answer here. Just you can check the answer yourself. Okay. Now, that is one of your homework problem. Find the area of surface obtained by rotating the curve about y-axis. Okay. For this one, here, let's try to understand the problem. Now, x is moving from 1 to 2. Okay. From 1 to 2. We don't know exactly how the curve is made, but when x is 1, then the value is 1 over 4 plus 1 over 8. So that we have here a point. Okay, that is from 1 to 2. Once x is 2, then now that is 16 over 4, so the 4 plus some small number, so that here it will be larger. So the curve is connected like that. Okay. Now that is rotated about y-axis like that. Okay. So for this surface area, now here that is, okay, the basic formula is 2 pi r ds. Okay, let's try to get it with respect to x direction integration. Then, now x is moving from 1 to 2, so that for each x, now rotation is from here 0, so that now here from here to there, that is now the radius is r, so that from 0 to 2, and okay, 2 pi x, that's r, and then now here you have to put ds. Okay, for this term here, square root of 1 plus the derivative squared, 1 plus the derivative is here now x cubed and minus, okay, 1 over 4, okay, 1 over 4 x cubed, right? Okay, squared. Okay, we have to do it. Now, if you do a little bit algebra, then this portion will be same as now x cubed plus that term squared. So that here we'll write down the result only from 0 to 2, here 2 pi x, and here that is now x cubed plus 1 over 4 x cubed and dx. Now from now on, the computation is quite simple, right? Okay, you can do it yourself. Okay. Okay, that's the end of chapter 6. Thank you.